An American philosopher by the name of Alan Bloom once said, "Education is the movement from darkness to light." And in the few minutes I have here, I'm hoping to enlighten you on light. You see, most of us see light as a means to see the world around us. We wake up in the morning, we turn on the light to find our way to the bathroom. Few of us realize that light is energy. In fact, the most abundant light source, the sun, emits enough solar energy to the surface of the earth each hour than the entire human population would need in a year. Think about that for a second. That's crazy. What if we could efficiently capture and use this energy? Unfortunately, the society we live in today is driven by the combustion of cheaper fossil fuels. The combustion of these fossil fuels leads to the production of greenhouse gases, particularly carbon dioxide. The increasing concentration of carbon dioxide in the Earth's atmosphere is fueling concerns about global warming, among others. So the question I propose is, what if we could capture this carbon dioxide before it gets released into the atmosphere and use a clean renewable energy source like light to convert carbon dioxide into other usable fuels or chemicals? In fact, plants are already masters of this to begin with. They use light to convert carbon dioxide into plant fuel and oxygen during photosynthesis. My research looks to mimic this idea by using light as a means to convert carbon dioxide into other usable fuels or chemicals. Now, unfortunately, carbon dioxide is a very stable molecule. So to do this, we have to use a catalyst. The catalyst here serves two purposes. The first is to capture the carbon dioxide. The second is to make it easier to transform the carbon dioxide. Imagine yourself trying to jump over a tall wall. We can envision a catalyst as a wrecking ball coming in to knock down some of that wall to make it easier for you to jump over. Now the challenge comes in finding the Goldilocks porridge of binding between the catalyst and the carbon dioxide. We don't want that binding to be too tight because we'll never get the carbon dioxide off. And we don't want it to be too loose because we'll never get the carbon dioxide on in the first place to be able to transform it. Once we have that Goldilocks binding, we use ultraviolet light and an electron source to convert carbon dioxide into formic acid, another chemical we can further use. Now, ideally, we would want to find catalysts that can undergo this photochemical process efficiently. That is, we want to find catalysts that are not destroyed in this process and are able to convert more than one molecule of carbon dioxide. Additionally, we'd like to make use of the most abundant light source, the sun. Therefore, we must consider systems that make use of the maximum solar output of the sun, which is visible light, instead of the ultraviolet light I alluded to earlier. So as you wake up tomorrow morning, I encourage you to open up the blinds, look out, and view chemistry in a new light. Thank you.